Good morning, everyone, and welcome to our ET Forum TED Talk. This is our initial session. And this series of webinars and workshops, whatever you might want to call them, is meant to provide information for new technologies or technologies that aren't implemented in your classrooms, in the technical programs in the state college and technical colleges, particularly in Florida. So we're starting off with our good friend Pete Sirac, who's going to talk to us today about coordinate measuring machines. And first of all, I'll do a little bit about FLATE and FLATE's role today. So I'll talk next slide, Pete. So this series is brought to you is hosted by myself, Marilyn Barger. I'm the director of FLATE, the Florida Advanced Technological Education Center, and Laura Sharp, my colleague here in Florida, who's the program director of engineering, manufacturing, and building arts at St. Petersburg College, which is just across the bay. And we've been trying to figure out good ways to provide professional development and the technical topics that the educators might need in manufacturing programs across the state. So this is where what we're trying to provide right now, and hopefully you'll give us some feedback on this kind of a session. Next slide. So FLATE is now, after 15 years of funding from the National Science Foundation, is now part of the Florida Makes Network and partially funded and supported by the Florida Department of Education under their Perkins 5 Act State Leadership Grant. So we're grateful for our partnerships and really looking forward to expanding our interactions with industry through their partnerships with Florida Makes. Florida Makes is the Florida Manufacturing Extension Partnership Center. There's one in every state, and they work with small and medium-sized manufacturers to increase their businesses and improve their businesses. So we're hoping to bring those folks together with our educators around the state to better improve the connections they have, and also, better prepare the students for going to work in those facilities. Next slide. So that's just our vision, to drive Florida's world-class manufacturing workforce education system. And that's what we're going to be working on with Florida Makes and all their partners. Next. We're continuing our three-pronged mission to provide good curriculum and do reform work in curriculum, provide professional development like we are here today, and also provide resources for recruitment and outreach to encourage more students to join manufacturing career pathways. Next, I'm going to turn it over to Laura to introduce our speaker today. Laura?
Thank you, Marilyn. Hello, everyone. Sorry I can't turn my camera on. It's decided not to work. It's Friday. But thank you for coming. And I have the honor of introducing our speaker today, Pete Sirac. He has a bachelor's degree in aerospace engineering and is the Quality Assurance Director at Seal Dynamics New Product Development Group in Tampa, Florida. Pete has 18 years of experience in aerospace design, manufacturing, and quality across various platforms, and has been an active member of the Bay Area Manufacturers Association, otherwise known as BAMA. Pete serves on several academic advising committees for local community colleges and is also the chair of FLATE's Industrial Advisory Committee. So to help Pete get started, we want to give him an idea of his audience. So let's start with a poll to find out if you have a CMM. So we'll launch.
Steve, can you launch the poll?
There we go.
So quickly, just pick yes or no. We'll just have about 30 seconds or less. It's a pretty easy question. All right.
Okay.
3. Go ahead, Laura.
Oh, no, that's okay. So Let's see. Oh, look at that. Everyone here does have one. That's awesome. So we're going to let Pete get started, but if you could, in the chat off to the right-hand side of your screen, if you could put into the chat what type of CMM you have, that would help guide the conversation as well. So Pete, it's off to you.
Awesome. So as she said, I'm the quality director here at CO Dynamics, and we reverse engineer aircraft parts and then sell them aftermarket. So a great deal of reverse engineering and quality inspection go on here. What I want to go over today in particular are the types of CMMs, the components of a CMM, the operating environment that a CMM should be working in, or some challenges that they might face if they're not operating in that environment. Sort of how a CMM works, part setup, and then initial part alignment. And I'll be using a couple different methods to go over these, both live camera review in this with the CMM here, as well as some pre-recorded video and PowerPoint presentation slides. I also want to point out that I am in a working active metrology lab, so please have any patience or if there's any distractions in the background if that should occur. So also too, it's important to know that as a CMM, a coordinate measuring machine, its goal or what it does primarily is to analyze geometrically and dimensionally, or establish the geometry and dimensions, and then analyze those of any object. That might be for quality inspection, to verify, validate a product, or for reverse engineering purposes, for example. So types of CMMs, one, cantilever, simple, really small, typically out on the shop floor. And you can see it's cantilever because the x-axis is out there, only supported on one end. This offers three sides of access for a user. The next one is a horizontal arm. This is also looks like a cantilever, but this typically has just like a scribe on the end, is often used for large sheet metal components, like say auto body parts, or even large aircraft body parts or something along those lines. The next one, the bridge, probably the most popular, most common, is similar to the one right behind me, almost looks exactly like it. The bridge CMM is probably the ones that you guys have in your own shops. And then few people see them, I've seen them actually, as a gantry. To give you a size, a perspective there, that's a person standing there. That's the only difference between that and a bridge CMM is the fact that the stands it's mounted directly to the floor typically. And obviously for much larger components, we had something almost as big as a gantry. It was actually the largest bridge that you can make. We would inspect the 60-inch turbine center frames for the GE90 engine on it, and a former life, that is. Other devices like CMMs, but technically aren't, like your articulating arms. Some of you guys might be familiar with the Ferro or Romer arm. And then there's some of these new products that have popped up, and these will fit right on your office desk. And these are both categorized as portable coordinate measuring machines. Very useful and have their own sort of niche uses as well. I want to show you guys a video here real quick. This is our metrology lab. You see him right behind me. Something I want to point out real quick here is down underneath is the controller. So we have the overall CMM, our computer and software up to the side, but down here is the controller, and that's something I'll be going over a little later. I just wanted to point out its location. You can see we've got the probe head. We also have a probe rack that allows for automated probe changes as well. This is the surface plate, precision ground. These are just ancillary devices that we purchased outside, separate from the CMM, that helps produce or improve productivity, allows us to move stuff around without necessarily breaking parts down. Something else I wanted to go over was in the components are the bearings. A lot of people work on a CMM and never understand sort of how it works. So these are some of the bearings that glide along this, in this case, the y-axis. Under here, the bearing on the other side. Now, what's important? A lot of people wonder, hey, I've got my CMMs running on electricity and compressed air. What's going to what? Well, these bearings are often ceramic, precision ground ceramic plates that have holes in them, typically like 1 or 2 holes that are hooked up to your pneumatics, to your compressed air. So the compressed air provide that cushion of air that those bearings that the CMM rides along as it moves across the various surfaces and your X, Y, and Z axes. And then your electric, the electricity is powering the motors that drive those that movement, that translations across those various axes. You got some other good views too here. Yeah, this Z-axis happens to be granite as well. Sometimes there'll be aluminum. Here are the pneumatics in the back. You can see the pneumatics in and the out into the machine. It's got some pressure gauges, some filters. There's some additional filters on the wall where the compressor's coming into the building. And I'll be going over some more of that later. Here's the Y-axis motor. Fortunately, serendipitously, a couple of days ago, we were having our machine calibrated and worked on. And so while it was apart, I took some of these pictures. Notice the Z-axis here. Again, we have several bearings all around the axis. And then this like copper colored strip is the reader, I'm sorry, the scale. And then this is the reader that provides the feedback from the scale so that the CMM knows where it is. This is our probe. So you've got above this was the probe head. You've got your probe module, the extension, your actual stylus. A lot of times when people say probe, they really just mean the stylus. It's actually a combination of all these things. In this particular case, this is a TP20, and you see the STD, the standard force. There's a sensitive, a not so sensitive. It depends on how long your probe is. And something else that you need to know, it's very important to know, is that when you touch, this in particular is a touch as opposed to like a scanning probe head. When you're touching, if you touch in the axis of the probe shaft, that takes 10 times the amount of force as triggering it in perpendicular to the shaft. And it's very important to know while you're setting up your program and touching off your part, is to the difference in force required between perpendicular and longitudinal or parallel to the shaft. In this case, it's a probe module attaches magnetically. That's that. I'll go back to the slide now. So I had a couple of questions actually I wanted to think there. If anybody, did we have polls for these, Marilyn? We're just going to ask the question.
I was trying to get unmuted. Now you can just go ahead and ask. I didn't insert polls here.
Okay. So some of the, just wanted to point out so that in review that the most common CMM was the bridge, and the compressed air is typically used to provide that cushion of air that the bearings ride along. In addition to the CMM, you've got obviously the software. In our case, we use CMM Manager. A lot of it depends on the CMM you get. Sometimes a CMM manufacturer will want you to use their software. Like Zeiss, for example, will have their Calypso. Brown and Sharp uses PCDMIS, but you can actually use various CMM software for any CMM. It's just what's the what kind of support are you going to get with that CMM software as far as technical support from the developer of that software and the machine too. So it's often good to use the software provided by the machine manufacturer. But like I said, we use CMM Manager. I highly recommend if you don't have anybody in your organization that is formally trained on that software, that you get them formally trained at least at a beginner and or intermediate level, so they're taking full advantage of all the capabilities of that software and that they're using it correctly. Because if they're not using it correctly, you could be getting data or analyzing data differently than it should be, and you might be getting incorrect analysis. So your CMM software doesn't actually talk directly to the CMM. It's not controlling the CMM motors and various components directly. It's controlling it through the controller. So if you think about the CMM software, it's sort of an interpreter. It takes what you're thinking in your head, translates it into information that the brain of the CMM, the controller, can understand, and then that is then made into electrical signals to the CMM's motors, various fingers, hands, and components of the CMM, so that it does what it needs to do to inspect the part. In our case, as I showed you earlier, we have this is our controller. It's got the various lights, and depending if they're lit up or blinking, tells you if something's wrong or not. Technically, the top part is the control, and the bottom part is a servo power amplifier. But it's when they work in conjunction together in unity that they're controlling all the components of the CMM. And so often, if you have a problem with your CMM and you have to talk to tech support, they're going to want to know what kind of controller you have. So it's important you understand how all that works and at least what kind of controller you have. Like, for example, in this case, it's some Renishaw UCC T3+. And that's important to know that. All right, operating environment. So in all metrology departments typically are under a controlled environment. And a lot of manufacturing shops have a controlled environment just because of the tolerances they're trying to hold on the product they're making can't stand, or they can't maintain those tolerances if your shop floor temperature is fluctuating, 10, 20 degrees or something of that nature. So temperature and humidity is probably the most critical, that's at least stable. And depending on the company you talk to or the ISO standard, it's around, often the standard temperature is 20 degrees Celsius or 68 degrees Fahrenheit. You can see here's the temperature humidity gauge, barometric pressure gauge that we have. It's nice because it's digital and it logs that data into a CSV file that I can pop into Excel real quick and take a look at over time if we're having issues or something of that nature. So if you think about too the temperature, if your components of the CMM are flexing and growing with temperature as well, that'll affect your accuracy of the machine, obviously too. Cleanliness is a big deal. Cleanliness doesn't affect the accuracy so much as the longevity. And that's important too, because if you're only getting your CMM calibrated on an annual basis, but it's out on the shop floor and it's open to a lot of, say, dust and oil and things of that nature, things could happen to it that calibration goes out. And if it goes out after 6 months, then you got 6 months of parts that may be, incorrect or bad quality. So it's important to keep your machine clean. We often wipe down the surfaces, especially the surfaces that the bearings are moving along and so forth. And don't forget about the air. When I mean the air coming in, the pneumatics. So you've got a compressor typically outside maybe. It's important that air is being dried first and cleaned before it goes into the compressor or after the compressor, but just as long as it's being dried and cleaned before it goes into your machine. Otherwise, those holes, the pneumatics of your machine will start to get gummed up, get algae in them, and things like that. It's a whole another deal, and it could be expensive. Vibrations are a big deal. Especially I've worked in a shop where we had very large mills, and we had a CMM right out on the shop floor. So before those mills went in, a large part of the concrete was dug up, relayed down with a barrier of a dampening material to prevent those machines from affecting each other, as well as the CMM around it. So that's important to understand that vibrations, especially an extremely sensitive CMM, can be subject to those vibrations, get false triggers and things of that nature. All right, so something I like to make sure people are aware of is, what does a CMM know? Just like, computers really only know one of two things, right? On or off. A byte is either on or off, right? So CMMs only know a couple things as well. The home and volume, so the home is typically at the top right corner, or back top right corner, and then its overall volume that it operates in. It knows the probe size, and then the location and center of that probe. It doesn't know where the sides of the probe are. It knows the center of that probe, and then through it applies the knowledge of its size to where it's touching the part. And then you can get into whole sign errors and stuff like that. But that's what's important to understand, that it knows where the center of that probe is. And then, of course, what direction it's traveling in, or its vector that it's moving in when it touches and triggers off a part. And so, because it only knows those few things, everything else it knows is what it's being taught by you as the programmer or from that CMM software. So be careful what you're teaching it. Often, if you're having a problem with a program, if you go back to the basics of what the CMM knows and what you're teaching it, you're probably going to find out more often than not it's what you're teaching it that's the problem. All right, so I made some assumptions there: home and volume, probe size, location and probe centers. Well, the assumptions there is that it's got some accurate information is there as well. So in our CMM software, and all CMM software, this is just how ours looks. You have to define those probes. So I have over here this probe rack. You guys see this? Yeah, you guys can see the probe rack here. All those probes have definitions, and you can see them right here: probe 2, probe 3, probe 4, and then we add that additional information for human sense, that we know which one, and we can easily line them up. Oh, this is the correct one, or whatever. But what's important is that each one of those has got some explicit definitions about it, and then ultimately, when you do probe tip calibration, which I'll go over too, it's fine-tuning that information. So that brings us to calibration. So there's actually two types of calibration. One is your machine calibration, where you get like a third-party technician that's something they focus, they specialize in, and they'll not only just calibrate to make sure that across the volume of your machine, they're verifying the accuracy, but a good technician will also do some preventative maintenance, some fine-tuning of the harmonics while they have some things open and stuff like that. If you've got a calibration technician that comes in and they're not doing some of those things, you probably need to find a new calibration company if they're not performing some of that PM work and that fine-tuning of the harmonics of the equipment. And it's typically performed annually. How often your organization does a calibration is really depends on your risk assessment as far as in the criticality of the parts you're making. We don't manufacture any critical components, but I've worked at facilities where they did rotating parts and jet engines, which are extremely critical, and so those calibrations were probably done more frequently. Certainly, the probe tip calibrations and how often we validated on a master part was a lot more frequent. Whenever you move it, so if you're doing a move from one facility to another, or maybe you're changing the environment, you're revamping your floor space at your organization, your plant. If you're going to move that CMM, it needs to be recalibrated. So don't get a calibration right before you got to make a move. Do it after, right? Anytime you get significant work done, if you got a repair, you need to do anything that's going to change the harmonics of the machine, definitely get it recalibrated. All right, so that's the machine calibration. And then often, a lot of you are probably aware that you do a probe tip calibration, where you get your cal sphere and you're probing you're doing calibrations on the tips. That is not a machine calibration. That is not verifying the accuracy of your machine through its volume. That is only telling the CMM software how big your tips are and where they are. That's all it's doing. But that's critical too. It's typically performed weekly. Some companies will do it daily, first thing in the morning. You know, on our Monday mornings, one of our quality inspectors will come in here and just run the programs, whether or not they are going to be inspecting parts on them that day or not. We just do it first thing Monday morning. It's a good thing, a good practice to do. Whenever you change a tip, and I don't mean like whenever I have the machine go and change from one tip to the other. I mean, if you take, if for example, something happens, you need to replace a tip, you want to design a new tip, put a shaft on it, you're going to change the geometry, dimensions, the features of this tip, you need to go and do a probe count. And of course, too, should you have a crash? I think everybody there's got a CMM. We've all done it. We've all crashed and broken a tip at once or twice, maybe even 3 times. But anyways, depending on how long you've been working with CMMs, it's an inevitable event. We make mistakes. So obviously, after you have a collision or a similar event of that nature, you need to do a probe tip calibration. All right, something that a lot of organizations should do but don't is have a master part. We use our training part as a master part. And what I mean by that is at some point in time, something might occur or a question might come up where somebody questions the validity of the inspection, the data that you're providing for a part, right? And, maybe it's a customer, maybe it's a supplier that supplied you with product, you're inspecting, you're saying it's not good, they're saying it's good, right? So, and then maybe something happened with the machine, you're not quite sure what's going on. And so if you have a part, a master part that you run an inspection study on, you do gauge repeatability, reproducibility analysis on, and then you say, all right, here's what it checks. And you take that data and you file it away and you keep it as historical data, right? Well, then at any point in time, if you question the validity of what your CMM is giving you, you can take that master part and inspect it and compare the current data to that historical data and see if there's any change, right? And typically you want a part that's going to use maybe several different angles, probe changes, different features, comparisons. This has even got, I got holes on the side so you put the head at a 90-degree angle or something like that. So those are all things that I can use to evaluate the validity of the data that's coming out of my CMM. And then I can show, hey, there's no change in the quality of the information coming out of my CMM. I'm pretty confident of the information that we're giving to you on this part. So depending on the company, again, the criticality of the part, you might have a master for each product line. Maybe the first article or something like that. So, but that's important to do if you're truly a quality organization. You're going to have something along those lines. Part setup. All right, so that was a lot of information. Let me before I get into part setup, are there any questions? Let me see here. I got to figure out how to open my chat here. Or if you're, Danielle, if you're monitoring questions, or if there are any for me, I can answer before we move on.
I cannot see any question.
Okay.
So far.
All right. So part setup, and first and foremost, when you're making an automated program, and I'm referring entirely to automated programs here, because this is a full DCC machine. Just about anybody can get up and manually, drive the machine using the joystick or whatever. But with regards to taking full advantages of the power of the machine, its uses, you want a fully automated program. And I've seen people, CMM programmers, write programs, they're like, oh yeah, the person needs to go and do some initial touches. No, a good program doesn't need a person to do initial touches. All they need to do is hit go, that machine goes inspect that part, you can walk away, come back and everything's done. You got a nice report, and a good program too will even dump that data, that digital data, into a place that can be, that you can use statistical process control analysis on and stuff like that. So, but that only works well if, one, you have a solid setup for the part, and it's repeatable. Definitely, it's got to be solid and repeatable, and you have got a really good initial alignment. So in this one, the nice thing about these devices here, these plates and so forth like that. So I can put a square on here, and these lock in, and there's locations for each one of these that allow me to put this part back in the same place every time, same place every time. That's what's important, because the CMM, you can program some variation, or you can account for some variation with the CMM, but if it's over here one time, back here another, that's not going to work. It's got to go back to the same place. It's extremely important that your setup is easily repeatable. Next, that it's sturdy, stable, and can handle the trigger force. There are some parts that if you just sit them down on the surface, maybe it's a really small metal ring that glides really smooth across the surface. You've got to clamp it down or hold it in some form so that when the probe triggers off of it, the trigger touch itself isn't going to move that part. So you got to have a nice, steady, stable setup. Fortunately, this part is pretty heavy relative to the trigger force, so it won't move it. Whereas you can see in the background there, I had an inspector inspecting some parts earlier, and there's some hold down devices and stuff of that nature that help hold the part down while it's being touched. All right, so easily repeatable, sturdy, and stable. When possible, mimic the design data. I'll be talking a little more about design data going forward. But I say when possible. It isn't necessary though. But if you can do that, definitely do it. Document the setup. Document the setup. That's really important to document the setup. Because a lot of people, they get a great setup, they write their program and they don't document the setup, and then so nobody can repeat it later on. So make sure you document the setup. And we've got an example of that. There's something I always do too, is just like when you're writing a paper or you're doing anything, write your own program, you're so intimate with you that things that are so, that seem so, sensible to you and are easy to understand, you don't necessarily write descriptions for it. And so when you bring somebody else in, they have to do it, it might not make sense. So something that I do is after I document the setup and write the program, I ask somebody else to come and try to duplicate it off the instructions that I've provided. And I tell them, hey, be hard on it. Don't be nice to me. If something doesn't make sense, you need to tell me I'm a knucklehead and do it. Because you want a robust, easily repeatable setup, and that includes incorporating the setup instructions, the documentation of the setup. All right, so I have someone test it. Now, here is an example of a part that we inspect. Let me show you a video of it actually being inspected. So this is a drag link on a thrust reverser for a CFM 56 engine, I think. So it's a little more challenging to set up. These are 3D printed parts, actually. I've got one of them right here. Highly recommend getting a 3D printer. So there's the inspection there. Back down, back to this. So here's some of the documentation for that setup. Notice how they're pointing out, they're giving instructions for how you set it up. Here's the devices to use, where's these plates, which ones are they located on the docks. You can see, locate, you got 3, 4, 5. So they make sure that they put this, because obviously if it's over one, the CMM is gonna come over here and crash. So They got to make sure it's in the right place. And the nice thing about CMM Manager, our software, is that we can put those directions, that documentation directly into the program. So when they run it, it pops up and shows them, oh, here's what I need to do. And you know, you can put any kinds of user interfaces and prompts typically in any software program to tell people, hey, check this, make sure you do this, you know, take this out of the part before you run it. So those are important, but definitely document your instructions. And if you can, put it directly in your program. Again, just to touch base too on 3D printing, this is something that would have cost me $350 to have machined. So right about the cost of the 3D printer. So you can get 3D printers anywhere from $250 to $500 that'll make this stuff all day long for you. And in the plastics, PLA plastic is extremely inexpensive, about $23 a kilogram. I think this was about 100 grams, to give you an idea. So I highly recommend getting just a nice, easy little MakerBot kind of thing to help you with your fixtures. All right, so that brings us to initial part alignment. What's important as a best practice, I mentioned earlier, use datum feature simulators. So a lot of people don't realize that, like say for example, if I have a drawing that identifies this face on this part as datum A, your primary datum, that's not the true datum. The true datum is when I set it down on this. This is a datum feature simulator per ASME Y14.5, right? Which is the Bible for geometric dimensioning and tolerancing. This is a datum feature simulator, right? We often use these as datum feature simulators, but their surfaces are a little mauled up. So it depends on, again, the criticality of the part. Otherwise, if there's a real critical part, I might take a stone over this, make sure it's good. But when I'm getting my data, when it goes and picks up on the software, I can see what the form control is to read out. But that's what's important to understand, that this is the true data. It's basically a perfect, recognized to be a perfect feature. In this case, a plane. This is the datum feature simulator that simulates this data that's defined on the drawing. All right. I highly recommend you read up on that on ASME Y14.5 if you've never really gone over that before. So use datum feature simulators when possible. It doesn't need your initial setup setup and alignment doesn't need to be the datum system of the design, because sometimes those features that are in your design datums aren't necessarily easy to grab or touch with your CMM. So often you'll use the really easy features to set up your part, especially the larger features. If you have a really small feature that's a datum and you can't back off a whole lot, then as far as an approach and stuff like that, and it can't account for location variation, then you might want to use larger features. So with that said, you don't necessarily need to use the datum system. Understand the types of features that in CMM world, there are various types of features. You have a plane, a line, and a point. So plane is pretty evident, I think. However, if you think about a line, a cylinder is what we refer to as a line feature, because it's defined in your CMM world as far as in location and stuff like that as the axis of that cylinder is a line. So that's what we refer to as a line feature. And then you have a point feature. So if you went and got just the circle of the cylinder, that's a point feature. So a circle is a point feature, a cylinder is a line feature. If I got just a line across a plane, that would be a line feature. And then of course you get a whole plane that's a plane feature. And so each one of those types of features provide you with the appropriate alignment. You typically need a plane, line, and then a point to determine your initial alignment in CMM world. Constraining the 6 degrees of freedom. This is both important in CMM language and in ASM, GD&T. On how you constrain your 6 degrees of freedom. So I'll go over a little more of that here. So if you think about your Cartesian coordinate system, your X, Y, and the Z, you can move, you can translate, move back and forth along each one of those axes, right? And then you can rotate around each one of those axes, right? So we've got 3 translations and 3 rotations. Those are your 6 degrees of freedom, right? And so a good datum system will define which of those translations and rotations are being constrained while you're inspecting the part. So I have here this is a sketch or a figure taken straight out of ASME Y14.5 with regards to the datum section. So if you look here, we've got datum A, which is the back face, and then we've got datum B, which is this hole here, and datum C. So datum A, think about this. If this is my datum A, like on this part, if I set it down here, what degrees of freedom is it constraining, meaning preventing you from moving in, right? Well, because I'm sitting down, I can't go up and down through this. I can't go through this plane. So it's constraining translation in the Z-axis. If this is my Z, that's my Y, and this is my X, right? But I can rotate around my Z, and I can move in my X, and I can move in my Y, but I can't rotate in my Y or my X. So it's constraining rotation around X and Y and translation in the Z. So it's constraining 3 degrees of freedom, right? Now, these are what we refer to as feature control frames. And these are the datums that are being defined at feature control frame. Your first is your primary, your second is your secondary, and your third is, tertiary, or your third, right? And by standard, by Y14.5, you have to have at least 3 points of contact on the primary, at least 2 on the secondary, and at least 1 on the tertiary. And each one of those are defining which degrees of freedom in the order in which they're constrained, so that when I inspect a part, it's the same as the way that you inspect the part. It's the same as way as Maryland inspects the part, right? So that we're all inspecting the same way and get the same data, because depending on how you set that part up, you could get different values depending on the shape and form of the part, right? So that's datums and degrees of freedom. So that's a lot of information. I hope I invoked some thoughts and some questions here that we can go over. And of course, I've got equipment right behind me. I'm happy to work with and even use to answer some of those questions. And the nice thing is too that I can pull my software up as well live too.
Thank you, Pete. Daniele, are there any questions?
Let me see the chat box. So please, this is the moment. If you have any question to ask, just type in the chat box, please. Just waiting a few seconds to see if anyone has a question.
So while people are writing their questions, Pete, I have one. So you are extremely knowledgeable about this. That's very obvious. And we thank you for this. How long did it take you to become this knowledgeable with this machine?
What time is it? Okay, so I think that we're constantly learning about this equipment, and I've had the opportunity to work in several organizations that had various types of equipment. So I can program in Calypso and PC-DMIS, worked a little with OpenDMIS on Wenzel, worked with Brown and Sharps, Zeiss, Mitutoyos, across various products. And so I would say that the full extent of my 18 years is and continues to provide more and more experience on these machines. And each new machine provides its own issues, and every time you get a software update, you'll learn more stuff about how various and different companies talk to their CMMs in different ways and have different requirements too. But I tried to show you this sort of the general information that's pretty much applicable across all platforms. Also too, something I mentioned to Laura and Marilyn is that unlike a car where you don't need to know how a car works to get up and drive it, a technician, a machinist off the floor doesn't necessarily need to know how a CMM works to run a preset program. They set it up, they run it. But a good programmer, a CMM programmer, really needs to know how the machine works, really needs to know how to troubleshoot issues when they pop up, because you don't always have, a third-party technician that's an expert on it, waiting around to get products up and running at a moment's notice too. So that's why I tried to go over some of the basic, in this first edition, to go over some of the mechanics and what's going on in the background in your CMM.
Fantastic. And just a follow up with that. So did you go to formal training on any of these machines, or was this learn on your own?
Yes. I've had formal training on this software. Some of the other software packages I used, I was at facilities where we had programmers that had formal training, so I didn't necessarily get formal training on that as so much as they provided me sort of OJT, but I wasn't one of the regular programs. Whereas in here, myself and Anthony in the background there, we both have had formal training, and then we share some of that knowledge with our people here. So all the inspectors here can write programs, at least rudimentary ones, but Anthony and I are the primary programmers. So whoever your primary programmer is should definitely have some formal training in that software, where you're not taking full advantage of it.
I'm sorry to interrupt. We have one question. I don't know if
Yeah, go ahead, Dan.
Answer. Did you ask that already, Laura?
I can't see the questions, unfortunately.
Oh, okay. So we have one question here is, did you make your test part yourself?
I'm sorry?
Did you make your test part yourself?
Oh, did we make the test parts? Oh, good question. So I started back here in 2016, and it was already here. I think they got this test piece when they purchased their CMM, the Wenzel back there, and ages ago. So like 10 plus years ago or something like that. So no, I didn't make it. But you can make your own test piece. I mean, your own trainer or whatever. And it doesn't have to be out of aluminum. You can make a trainer out of nylon, hard plastic or something like that. Highly recommend having something like that.
Okay, I have another question. I'm just trying to make it larger so I can read the entire question. Nicely done, Peter. How detailed is your standard work? Do you include, now I need to open it, time, gosh, sorry, I have to read just, I don't know how to make it larger to read the entire question. Bill, this is your question. Could you retype your question in the chat box? I may be able to read it all, the entire question.
I can read it, Daniele.
Question. Okay, please, Stephen.
So the question is, how detailed is your standard work, and do you include time studies?
Good question. So it's as detailed as it needs to be. So some parts, like a part like this, probably don't have a lot of work instructions for it, right? Just this trainer here. But the components in the back. Some of these have been moved around. This is a little more complicated. These have been custom design supports and stuff like that. Those instructions are going to be a little more detailed. And again, it comes down to having somebody test it, right? So the person that was running this earlier, just before we logged into this webinar, was the inspector that was running it. These parts didn't write the program, and so if something comes up, he's got to go to that. And so we might even make more adjustments as it goes along. We do. I've got my CMM screen shared here, and I think I have it. So CMM Manager has a Visual Basic interface, and so we collect start and stop times, and then what the duration of that run, and it comes out on the report as well. It'll print out what the runtime is. This is just a general, so it's not shown right there. but we'll print the runtime and actually, and then I have the CMM send that data, that digital runtime data, to an Excel spreadsheet that I collect, right? So every once in a while, I'll go and look at that, and I do it more, not necessarily by part, because the breadth of the product that we make here is huge. I think we have 1,400 parts on the catalog, and so any one particular part, I'm not really doing time studies on. For me, I track it more for capacity. You know, how much capacity am I using on the CMMs? So when somebody says, hey, do we need another CMM? No, I'm only using 20% capacity right now, right? But in a shop where you're only making 5 or 6 parts, you're darn tootin' I'd have some time studies, right? Because you guys are really monitoring activity, and you want to know one time you run it takes 5 minutes, another time it takes 10 minutes. Hey, what's going on there? So yeah, definitely. And typically, any CMM software, there's a way to track how long, the duration of any particular inspection. I hope that answers your question.
I didn't even thought of that. So I'm glad somebody asked that. Daniele, is there any more questions?
Okay, yes. I'm gonna run the same issue, Stephen. I don't think I can read them.
I can see it, Danielle. What are some common problems you run into? This is from Shirley, I think. What are some common problems you run into and mistakes that someone might make using a CMM?
So I think probably one of the most common problems are when you have somebody that's doing their writing the program, and they set their initial alignment up, and they don't understand how they're doing their alignment and what they're thinking in their brain and what they've actually told the CMM. And then when they go and run their part, the CMM crashes into something. That's all. And so often even when I run a program the first time, I'll turn the speed way down and make sure it goes okay the first time, right? So whenever you're going to have whenever you get the interface between the human interaction and the CMM, because the CMM, just like any computer, is going to do exactly what you tell it to, right? I've run this program several times, but I'm not fully done with it, and because I'm constantly moving stuff around here, that first point, I always turn it way down. But I think that's probably one of the most, to me, what I see. What do you think, Anthony? What do you think the most common?
Alignment.
Yeah, alignment.
What's set up there? You don't follow the instructions on how to set it up.
Yeah.
The way that it's saying exactly.
Which falls in line. So that initial alignment, if it's not set up properly. So whoever wrote the program and documented all that setup issue, all that setup, if that's not repeated, remember that CMM is going to go. You tell it to go to 5, 4, 3, XYZ. It's going to go there every time. So if that part isn't there, there's going to be a problem. That's probably the most current. And unfortunately, stylus, that little stylus on the end there, that's a ruby, synthetic ruby. But that one little tiny component is about $115. So yeah, breaking one of those a lot can get costly. That's a really good question.
So we probably have time for one more question.
I have a question. If there's none others in the question box, Laura, look in the question box. That's where I finally found the input from the audience.
I can't see anything.
Can't see the questions either.
No.
Okay, we'll work on that. So Pete, what kind of training, what kind of background do the folks who are running those that you're supervising or directing in your shop there? What's their background? So we're talking to community college faculty, maybe bachelor's level engineering technology faculty. Is this something for their?
A broad range of inspection or backgrounds. I mean, Anthony's one of our primary inspectors. He's got a bachelor's degree in English. No, history. I'm sorry. history. But he ended up leaving that industry to come in. He's been in inspection now for 7, 8 years. Yeah. But, and certainly started programming long before that. I don't think it's so much the background as, like I'll hire somebody that has zero quality experience if they have the aptitude and the attitude, because I can teach them to do a lot. I think what's important is that people, that a person that does that is open and can absorb the information and have the aptitude to learn it. But it certainly helps if they have metrology experience, inspection experience, and working with height gauges or just micrometers, calipers, and things of that nature, so that moving over to a CMM and learning stuff, understanding X, Y's, and Z's and geometric dimension and tolerancing, I think that certainly helps and it is a big jump. It helps get rid of or reduce that learning curve. But I mean, we've taught all kinds of backgrounds here. I couldn't tell you any one specific.
Okay, great, thanks.
I'm sorry, that is a tough question to answer.
Well, we're trying to, prepare students to go to work. So it's always a question that I think educators have is, am I doing the right thing? How pervasive is this in the industry? Do my students need this skill? Do some of my students need this skill? Maybe not all of them.
This is definitely an important skill. Like I said, all of my inspectors know how to use this equipment. Not all of them can program it well. They can all do some rudimentary stuff. There's just a couple of us that can write the more complex programs. And I mean, a good CMM programmer on critical components like turbine airfoils and stuff like that, turbine blades. I mean, those guys command an extremely handsome salary. Or gals, I'm sorry.
Yeah, thank you.
Thank you. So can you stop sharing your screen, Pete?
Okay. Yep.
And we'll go back to the original presentation.
We have the original.
I have the original.
Oh, okay. Well, if you want to put that up.
But yeah, go ahead and put it back up.
Okay.
All
You guys see
right.
it?
Yes, thank you. I can see it. I'm hoping everybody else can.
Yeah.
Yes.
And I don't think we mentioned this at the beginning, but some of you may have found it. This presentation is in the handouts portion of the contents on the right-hand side of your screen. So if you pull down that box, you can actually save this presentation, but also the link to this presentation and everything else will be sent out to everyone as a follow-up as well. So just before we close out, we wanted to provide you with some resources. The first one, many of you probably are familiar with. This was started by Department of Labor TAC grants, is skillscommons.org. There are just literally hundreds of free lesson plans, labs, and activities, and many of them have to do with the topic that we talked about today. So if you want to expand maybe on some of the things that Pete was talking about or start including those, but you need a little bit of help getting started, that might be a good place. Also, I included the Faro Training Academy. So the reason why I put this here, I know not everyone has a Faro arm, but they have free videos on, how to do setup, how to test out a probe, those kinds of things. And so again, especially with a lot of us being remote, this might be something useful that you could use as a resource for your students. Also, there is a really interesting article in this Metrology News. It was published about 6 months ago, but it's relevant, and it talks about the future of CMM. And not only just in technology wise, but where it can be used. So it's a really interesting article about a lot of the non-traditional kind of manufacturing areas that CMM is probably going to be used in. And then there's a YouTube channel here as well. If you want to check it out, they have a lot of videos as well on all different types of CMM material and manufacturers. And so again, it could be a resource, especially if you are teaching remotely. Next slide. So Marilyn and I have worked on providing 3 of these this semester, this spring semester. And so we wanted to invite you to the next 2 to look forward. And so the next one will be on Friday, February 26th, same time, 9 to 10 a.m. And this one will be featuring Bill Mazurek, who is the president and managing director of Maztec and Associates. And this one will be on tools to better implement root cause analysis. So we're kind of staying in that realm of quality, but it can definitely apply to a lot of different areas. So we hope that you will join Bill and the rest of us on February 26th. And then the third one will be on April 23rd. Again, the same time, 9 to 10. This one is with Mike Ennis. He is Florida Makes business advisor at the Manufacturers Association of Florida Space Coast. And this one will be exploring OSHA, which I teach industrial safety, so I can't wait for this one. So I look forward to his talk as well. So the registration links are there at the bottom of the slide. Again, you will be able to get a copy of this slide if you can't pull it off the table of contents off to the side. And also everything's at FLATE.org. And the last slide. And so we really want to thank you all for joining us on our inaugural Tech Talk. And we hope that you found it informative. Pete, we can't thank you enough. Your knowledge is definitely made us smarter today. I definitely feel more informed, and I feel like I need to take a class as well. And a big thanks to Marilyn for helping us organize this through FLATE and Florida Makes. And thank you to the Florida Makes people as well with helping us with the GoToWebinar platform and hosting this talk. Marilyn, do you have anything you want to close this out with?
No, thanks again to everyone for joining us, and Pete and the rest of the speakers coming up. We're excited about this series and hope there's some things you can take back to your classroom, including just having your students watch this recorded session, minus the intro slides from about us and FLATE, but maybe some opportunities for you to help your students get ready to explore this particular technology. And have a great weekend, everyone.
Have a great weekend, everyone. Thank you.
Bye.
Bye, thank you.